And we are live.
Hooray.
All right. Hi there, I'm Frank.
Hi there, I'm Jackie.
And there's two of us. Hopefully the other two will join us here shortly. So this is our second Google Hangout for Astronomy 111X, the Global Freshman Academy course, ASU and edX. So let's see, just a few things, then I'm going to turn it over to Jackie so you can get some tours and other stuff. Let's see, so this is the last week of the course. We're in exoplanets, and then the following week is when you have your final exam. I believe you've got all week to do that in a 3-hour sitting, proctored if you're taking it for credit. Let's see, the final exam will be comprehensive. It covers the whole course, and it's at about the same level, and quantity is your assignments and other exams. Let's see, if you've got any questions you want to ask, the chat window is open. Go ahead and enter in your question there, and we'll see if we can take it live. Otherwise, I'm going to turn it over to Jackie for right now.
Okay, so can you hear me good?
I can.
Okay, so there may be a slight delay when I give this presentation between things I show you and it coming over the visuals. And that's probably going to be happening. Hey, how do I go to full screen? Because you've kind of got the dominant screen right now. Hi, person.
Maybe if you hit screen share, maybe?
No, that's not right.
Well, if you're talking, you should have the dominant screen.
Right? I don't seem to. Maybe all shrinky.
Yeah, you do. When you're talking, you have the dominant screen. So I'm going to mute so you got it.
Okay, great. Okay, so I am currently on Mount Graham using a telescope. I'm using a 2-meter telescope, which is not big as professional astronomical telescopes go, but much bigger than any telescope you're likely to use, except perhaps at like a university event. But even then, you're probably not going to use a 2-meter telescope. Most people use like a 20-inch. So here's the control room, and I don't have a GoPro, so it's going to kind of always be over my shoulder here. So this is the control room of a telescope on Mount Graham. It's called the Vatican Advanced Technology Telescope, or the VAT for short. And to prove to you that I'm on a mountain, well, first of all, here's Gary.
Hello.
Gary's one of the mountain ops staff, and he's going to help me actually show you the telescope. And I'm going to go out the balcony here and show you the other telescopes very briefly. So there are 2 other telescopes on Mount Graham. The one with the kind of green roof, which unfortunately is not facing us, which is too bad, because it's actually open right now and observing. It has a beautiful silver dish, quite a large silver dish. It's about 15 meters in diameter. And what kind of telescope? Frank, would you like to tell us what kind of telescope can observe in the middle of the day with the blue sky open?
It's sunny.
Yeah, it is sunny. But the telescope's not pointing at it. So that is the sub-millimeter telescope. That is a radio telescope. It actually looks at microwaves. And then beyond it is the LBT, or Large Binocular Telescope. All of these telescopes are operated by the University of Arizona, which is our sister university, ASU's sister university down in Tucson, as opposed to Arizona State, which is in Phoenix. Easy to confuse the two. And the LBT is an optical telescope. It's a visual wavelength telescope. It's closed right now because telescopes that use visible light don't observe during the day. They only observe at night. But it's actually got 2 8.4 meter mirrors in it. It's a very large telescope. My telescope structure, can you see the dome from here? Not quite. I'm gonna have to go upstairs to show you the actual telescope. I'm in a cozy little telescope that has an espresso machine, which is considered the height of luxury for telescopes and observers. Gary, can you man the brake? So Gary's gonna man the mirror cover and the brake, and I'm gonna go upstairs and I'm gonna fill the camera with liquid nitrogen, and then Gary's gonna open the mirror cover and turn the brake off, and then I'm gonna yell at you to turn the brake back on when we're done, so that it doesn't fall on my head. Okay. So now we will wait a second for the world's slowest elevator. This is the room full of computer stuff that controls the telescope, including the servos. There's an uninterruptible power supply in there, so that if we get struck by lightning, the telescope won't be zapped. This is a $5 million camera in there. Here I am in the elevator. Hopefully we won't lose our microwave connection while I go up there. And here, this is a dewar of liquid nitrogen that just happens to be in the elevator. Because we just changed the tanks. So now I'm going into the main room with the telescope as soon as the world's slowest elevator opens up. So I've gone from the second floor to the third floor, which is where the telescope lives. And here it is. Is this still working, Frank? So
still working and very cool.
Okay, so here we are. Frank has shown you the Discovery Channel telescope, which is it's up near Flagstaff. What's the mountain called again?
They don't tell you the name of the mountain.
Oh, Lowell Observatory. It's on some
Lowell
mountain.
Observatory. They don't tell you the name.
This is actually a very compact telescope, and I'm going to try to point out some important things about it. At the bottom here, where's my finger? All right, this is the camera of the telescope down here hanging off the bottom. This big circle at the bottom is actually hiding 2 meters of glass, and that's where the primary mirror is, and I'll show you that in a second. And then it's actually quite a compact telescope. You might be able to see the secondary mirror up at the top. So it's only about as tall as it is wide. So I'm going to go up these stairs. And here's the sister.
So Jackie, why don't you say a little bit about what it is you're observing?
Oh, I'm observing galaxies. And I can show you some of that data in maybe 10 minutes or so, if you're interested in seeing it. I'm looking at nebular emission from galaxies outside of our own, which is not a topic we've covered in our class because we're all only doing planets, but that is what I'm looking at. And here's the camera, and it's connected to one of these tanks of liquid nitrogen, and I will quick fill it. It'll be a little loud and a little dramatic. So now there's smoke coming out of my camera, except it's not smoke. That's nitrogen gas. Inside the tank here, the gas is actually liquid. And so that's, minus 70 degrees. Kelvin or Celsius? Good question, probably Celsius. And it's coming out the bottom of the telescope, outgassing, and it'll start dripping the liquid in a second. So now it kind of looks like I've got my own science fiction movie going on here, a little cloud machine. This is also a good way to make ice cream, but not with the camera. So astronomical cameras, professional ones, tend to be cooled with liquid nitrogen. And that gives them a better performance than you would normally get. And now I'm going to detach this pipe from the camera. All right, and clear it. Hey, Gary, can you open the mirror cover?
Okay, I'm gonna open it.
There's an intercom. Okay. So, Gary's now opening the mirror cover of the telescope. So in a second, we'll be able to see it. But I had to detach the camera first. And this is the slit of the telescope that I'll need to open tonight to look out. All right, can you take the brake off? All right, now things get exciting. So I'm going to pull this telescope down to show it to you. By hand power. Hi, Brent. And here we have 2 meters. How big is it compared to my hand? Here we have 2 meters of aluminized glass. That's the primary mirror, and the light hits that from the sky bounces up to the secondary mirror, and then it goes down back through the hole in the mirror to the camera at the bottom, which is now a very chilly minus 110 Fahrenheit or Celsius. I don't know. I'll have to look that up for you guys.
How often do they recoat the mirror?
You know, I think they usually do it every few years. I'll have to ask Gary that question. So I'm going to return the mirror to its position, and this concludes the tour for now. And I'll be back in a little bit.
Okay.
I have to put everything back where I got it.
That's cool. So this will be a good segue for Brent to pick up one until you come back on.
Okay.
Pulsars, planets, something like that?
Yeah. So there's a question about pulsar planets, and I wanted to talk about just briefly how they were detected and maybe their formation and the formation of pulsars also. It's pretty interesting. So what I learned is that pulsar planets were actually the first exoplanets ever detected. The first time they were actually detected, this was in, I believe, the early 90s, or it could have been actually in the late 80s. Oh, okay, it was 91, that's right. And this first planet was actually disproven, but then a year later, 92, two more planets were detected orbiting a pulsar, and these were actually confirmed to exist. So the way they detect these pulsars, planets, is that pulsar is basically a neutron star, and it's orbiting really fast. And these pulsars are actually millisecond pulsars that have planets, meaning that they rotate every millisecond, basically, or less than a millisecond even. So basically, they look at these. Every time they rotate, they're kind of shining some radio light at you, and they do this very regularly. Like, their rotation is very precise. Like, it doesn't change very often. It slightly decreases over time, but this is like over many years that you'll see this slight decrease in its rotational period. And when something's orbiting the pulsar as it's rotating, they see a slight Doppler shift in its timing and the actual frequency of the radio emission from the pulsar. And they see the Doppler shift in a regular pattern, so they know something must be orbiting it. So this is how they detect the first exoplanets. So they found two orbiting a pulsar in Milky Way, and 2 years later they found a third planet orbiting this pulsar, and they're actually quite low mass. They're around 4 times the mass of the Earth, and then there's actually the third one that I mentioned that's orbiting this pulsar is about the mass of the Moon, actually. So this is the smallest mass exoplanet we ever detected. And then in 2003, there was a fourth pulsar planet discovered. This is a larger one, about the size of Jupiter. 2.5 times the size of Jupiter, actually. And then there was a fifth exoplanet detected orbiting a pulsar. This planet, though, is kind of strange. It's not what I would call a planet, really. It's basically an irradiated white dwarf. Basically, the hot outer shell of the white dwarf was blasted away by the supernova that created this pulsar. So I guess I should talk about formation of pulsars a little. So basically, a pulsar is a neutron star. That's what I mentioned, that it's orbiting really quickly or rotating really quickly. So what happens is that these really massive stars, either 8 solar masses, meaning like 8 times the mass of the sun or larger, once they run, well, once the core forms a lot of iron, it can't really fuse the iron without losing energy. And what happens is once the core is full of iron, basically it gets crushed by the gravitational force, and the only thing that's preventing the collapse is electron degeneracy pressure, which is it's a quantum mechanical law that says that electrons can't be in the same place at the same time, and so that's the only thing that's preventing the collapse. And then once the gravity gets too intense for that pressure to resist the collapse, basically the core kind of collapses into a bunch of neutrons, because the electrons and protons pretty much fuse together. So then you have this core of neutrons, and it's not pure neutrons, of course. There's like ions and electrons floating around, and well, once this core forms, it kind of collapses and shrinks, and then there's all this matter sitting outside of the of the neutron star in the core from the rest of the star, and then basically that outer shell of the star collapses down just from gravity and kind of hits the neutron star but bounces out, and that's how you see it, a supernova, the core collapse. And basically once it blasts off its outer shell, you're just left with a very compact, very dense neutron star. And whatever angular momentum the neutrons or the progenitor star had, it maintains that angular momentum, and because it's so small, its rotation speeds up quite a lot because it has to conserve the angular momentum that the larger star once had. And basically, if a neutron star has a neighbor, like in a binary, when that neighbor gets too close in this region called its Roche limit, it'll start accreting, meaning it'll start pulling material off of that neighbor star, and it'll basically start just sucking all that material in, basically, just through its gravity. And while it's accreting this material, it's actually speeding up. The angular momentum is being transferred to this neutron star and speeding it up, and that's how you get these millisecond pulsars. So I guess it's no coincidence that the millisecond pulsars have planets, because they were in a binary configuration. So that leads into how these planets actually form in a pulsar binary star. So there's 3 ways that it's been discovered that the pulsar planets form. So the first pulsar I mentioned that has 3 planets detected in the 90s. Basically, those planets formed from the debris that the companion left over when it went supernova, which is pretty interesting, I think, because basically the planets formed from the debris of another star, and it didn't form from the debris of the star itself. And I think I read that these were some of the oldest planets detected to exist. Let me confirm that. Yeah, actually, so I think, yeah, the third, or I should say the 4th planet detected orbiting a pulsar. I'd give names, but the names are just, they're not unique really. They're PSR, so PSR and some string of numbers basically. But the 4th planet detected, I'll just say the 4th planet chronologically detected orbiting a pulsar, that's actually the oldest planet ever known. Currently, it's 12.6 billion years old. Not exactly sure how they discovered this, but this is the 2.5 Jupiter mass planet. And then, yeah, this is another planet that formed from debris. Or no, I'm sorry. This is a planet that was captured. Basically, the way this planet formed, the 4th planet detected, it was basically captured by well, it wasn't, the planet itself wasn't captured. The system was captured by the pulsar. This this 4th planet was previously orbiting a white dwarf, and both the white dwarf and the planet were captured by the neutron star. And so that's another mechanism for forming a pulsar planet, is just you can just capture another solar system. And then there's another way, which I kind of briefly mentioned, where a binary system where you have a pulsar and a white dwarf can form. So a white dwarf is what you get after a solar type planet like our own runs out of material to burn, and you get this compact core of carbon, oxygen, and nitrogen, and it's what's left after that those solar mass stars have form a planetary nebula where it just sheds its outer layers, and so basically you had a star that went core collapse supernova, and then its companion went into a planetary nebula, and then you're left with this system. But somehow this Jupiter mass planet was left over after all this this violent formation, and it's pretty interesting how it was captured, and it's still there orbiting both the white dwarf and the pulsar. and they were able to discover it orbiting the pulsar from the Doppler shift. And then there's the other way I mentioned. This was in the news a couple of years ago. They called it the Diamond Planet, and that's just where the companion of this pulsar was the white dwarf, and basically the core collapse blasted off the outer layers of the white dwarf, and you get this really cool, basically diamond core left over, and it's not really hot anymore. It's just kind of like a cool core now, because most of it was blasted away from the core collapse that formed that neutron star. So that's really only the 3 ways that have currently been discovered that can form these pulsar planets. So I guess that kind of concludes what I wanted to talk about. Did you guys have questions? Did I get that all right in the formation of pulsars, Frank?
Good enough. It's live.
Yeah.
Did you say electron degeneracy pressure for the pulsars?
Well, not for the neutron star. That prevents the neutron star from collapsing. That's actually neutron degeneracy pressure, but to prevent the iron from fusing, that's the electron degeneracy pressure.
Okay. Okay.
Okay. Thank you, Bennett.
Yeah.
Movies. Let's do movies.
Oh, dude, can I show you the data?
Of course.
You'd rather talk about movies than my data. I see how it
I
is.
definitely want to talk about your data. The stunning quality of this data.
Yeah.
The signal to noise of this data is just outstanding.
Yeah. Yeah, yeah, so I have blobs that I look at, and I take away I subtract blobs from the blobs, and then we have different blobs. So I'm going to do a screen share to show you the data that I took at this telescope that I was just showing you. And this is actually data from last night. So we're going to do a desktop screen share. Yeah, there you go. Okay. And did that work? Am I screen sharing? Is it big, or am I in like a little corner again?
I see a big picture of me.
Yeah. Okay. Now, do you see a thing?
Yes, I see
A square? Yeah. Okay.
Okay, I'm muting.
Okay. I'm not saying that you always take over, Frank, but okay. All right. So these are some data that I took yesterday as a galaxy, and the galaxy's name is Sextans A. And this doesn't look like a lot of other galaxies that you may have seen. It doesn't have the cool spiral structure because this is a dwarf galaxy. It's a tiny little galaxy that's perhaps a 20th, possibly even a 50th the size of the Milky Way galaxy. It has a 50th of the number of stars, and it doesn't quite have enough mass to pull off the spiral arms. It's trying. It's got these little areas in here that are brighter, and I don't have color images yet, but these stars are very, very blue. This is a very young galaxy that's currently undergoing new star formation, and I think one of the questions that we did have in our list of questions was, how do nebula form? And actually, I can talk about that a little bit when I show you this, but like all galaxies, it has most of the light comes from stars, but some of the light is also coming from nebular emission. I'm interested in the nebular emission in dwarf galaxies because dwarf galaxies are very different environments from the Milky Way galaxy. Dwarf galaxies often are we say low metallicity. They have very low iron relative to hydrogen, but they also have very low oxygen relative to hydrogen. They have very low everything relative to hydrogen and helium. They're very primitive sort of environments. They're not necessarily going to be great at forming planets, but they are very comparable to in their astrophysical quantities and the way stars form. They're very similar to the earliest galaxies that formed at the beginning of the universe directly after the Big Bang. So that's kind of why I'm interested in them. So I have here 2 images, and I'm sorry, like there's actually 2 CCDs. There's two detectors in this camera, and they're not quite at the same balance level. So this is a image that I took with what's called a narrowband filter, and this is an image that's centered on oxygen 3, and I'll show you what oxygen 3 looks like. So when you look at pretty pictures of planetary nebula, for example, this is not a star formation nebula, this is a star death nebula, this is a planetary nebula. This is how the sun will die, and this is the Ring Nebula. Everyone knows and loves the Ring Nebula because it's really pretty. All of these different colors actually are emission from different chemical species, and usually when you see a nebula and you see green like this, that's coming from oxygen. So my data that I'm showing you today concentrate on isolating that oxygen emission and pulling it away from the other things, including starlight. There's a little tiny blue star in the center there that's actually emitting all colors of light. And then the red light is usually going to be hydrogen emission. And there's different physical things about temperature and the electron density and the plasma that'll affect how much oxygen you see versus hydrogen, in addition to the total amount of oxygen versus hydrogen. So it's actually quite complicated. And then planetary nebula this is what it actually looks like when you take a spectrum of it. So instead of seeing the sort of rainbow that you would see with the sun, you actually only see like 2 bright lines of green, a couple of bright lines of blue, and this big red line. So my narrowband filter is basically a piece of glass that isolates only the light around the oxygen lines, throws out all the rest of it. I also have another filter which isolates the blue light over here. So I only look at the starlight and I don't see any of the gas. So this is my oxygen filter. So it does have stars in it, because stars are also emitting this light. And then it's got the nebular emission. And then I took a second image. This was 20 minutes actually. And then I took a second image which has no nebular emission in it. This is the blue light from the stars, but there's no nebular emission because I very carefully picked a narrowband filter that doesn't include it. And then what I do is I subtract them, ba-boom, and if we zoom in on these stars, you'll see these stars are kind of, suddenly they've got little negative ghosts around them. So I've subtracted off all of the starlight by subtracting those 2 images, and now I'm just left with the nebular emission. And can I zoom in on this and actually have it work? Sometimes this works. Yeah, this isn't really great resolution. So on my other computer, this looks a little better. But yes, these are all star-forming nebulas around the new stars that are, so they're having supernovae in them where stars explode. They're brand new stars in there. And the question in the forum was, I'm going to end my screen share while I'm at it. How do nebulae form? And there are different kinds of nebulae. There are supernova remnants, which formed because a star went kablooey. It's usually a massive star and blew up. There are planetary nebula, like I just showed you, and those form when a star like the sun dies and it sheds its outer layers. Both supernovae and planetary nebula are very efficient ways of moving enriched gas back into the interstellar medium, and eventually, hopefully, it would get picked up by and when I say enriched, I mean it has more oxygen in it, it has more iron in it, things that we need to make planets, things that we need to make planets with water, and things we need to make life. And then that stuff will then get reincorporated into a star-forming nebula, and the star-forming nebula just picks up all the gas that's going around and collapses under its own weight to form stars. And hopefully those stars will have picked up some of that extra iron and oxygen, and they'll form planets. Because the first generation of stars probably wasn't very good at it, but we're on like the 4th, 5th, 6th, 7th generation of stars now. So, okay, I'm done with that.
Okay, cool. I'll cover one of the questions in there. So the question is about something I posted a little animated GIF to, which was 3753, and I'm sure I'm mispronouncing this, Corunthe, which is an asteroid that's in a 1-to-1 orbital resonance with the Earth. And so the question is, how can such a body come into existence? Was it there before the late heavy bombardment? Can it be classified as an asteroid? So first, it is classified as an asteroid, and you get that from taking spectra like what Jackie just showed there, and from the spectra of the surface properties, you can deduce that it's asteroid-like, and so it's an asteroid. Things that are in the orbit of Corunthe don't last very long. You can do dynamical calculations, and typically those things are only going to last about 100 million years before they get booted out of its current 1-to-1 orbital resonance with Earth. So it hasn't always been there. It certainly hasn't been there since the late heavy bombardment. It's a relatively recent addition, and it's not always going to be there. It'll get booted out at some point. So exactly how it got caught is a subject of active research. So I don't think we can say definitively exactly where that asteroid came from currently, or where how it got put into that 1-to-1. But it is there, and it is interesting. So that's what I wanted to say about that one. Let's see, we covered the nebula, Jackie's Graham. Yeah, I could say something about the, quote, gravity waves, end quote, on Pluto. So unfortunately, there's two different terminologies, or it's the same terminology for two different phenomena. On the one hand, we had the very famous example of gravity waves this year, the discovery of the coalescence of two black holes sending out ripples in space-time. So that's one kind of gravity wave. That's the famous kind. And then there's another phenomena which are also called gravity waves, but what they really, perhaps we should rename them is to buoyancy waves. So these happen at the interface. They happen all the time, for example, at the interface between air and the ocean, or air and a lake, or something like that. And so you get these bounces in the atmosphere or in the water due to the fact that the material is buoyant. And so one of the things that they found at Pluto, as New Horizons went by and they were imaging the atmosphere as it went by, you can detect this rippling, this bouncing from buoyancy waves, aka gravity waves, in Pluto's atmosphere. And this is interesting, this is good, because it can tell you some of the properties that you wouldn't otherwise ordinarily be able to get using if the atmosphere was just sitting there. So the fact that Pluto's atmosphere is in motion tells you things about Pluto's atmosphere. That's what I had to say about that one. I think we covered them. Then, of course, we had the very misleading ESA thread of Venus being very cold at the poles. Well, yeah, if you're 140 kilometers off the surface, it's cold. So, yeah, ESA's PR needs a little work on that one. Okay. I think that's what I had to say on that. So, Jackie, did you get to watch Interstellar? You're muted.
I did.
You
I
did.
see it.
Excellent. Did you like it?
I liked it a lot, and I actually had to like outsource some of my physics criticisms because I was just so, it was really, really good.
Yeah.
And they're very daring with the physics in Interstellar. I think that they basically structured an entire story around relativity, general relativity, and special. And that's a daring thing for Hollywood people to do, and they did consult with Kip Thorne in doing it. And so I noticed a few things while I was watching it that bothered me, and then I completely forgot about them because I was just so swept up in the story. And then I spent the last half hour like crying my fool eyes off. So so then I had to go on Facebook and ask my astronomer friends, like, hey, can you guys remind me of what's wrong with Interstellar, which they were good enough to do. Shall I start with Gravity
Yeah, sure.
or
All yours.
Star Wars?
Whatever you
Yeah,
want.
so Gravity, so I'm going to talk a little bit about Star Wars briefly. The thing you have to understand, there's a difference between sort of hard science fiction like Gravity or The Martian, which I'm not going to discuss because I haven't seen it yet. But these are hard science fiction where they're really trying to be pretty rigorous in talking about a phenomenon that's astronomically relevant, versus something like Star Wars, which is really more strictly space opera or space fantasy. So there is a lot of astronomy in a show like Star Wars, but the expectations, like the bar for where I've got like what I expect to be correct, way, way lower. Where Gravity actually is pretty cool. I'm going to actually do some screen shares here in a second. Gravity, and oh, by the way, this is a good time for me to say spoiler alert. So if you haven't seen Gravity and you think you'd like to, I'm going to give away like the main plot point in the next like 1 minute. So skip the next 3 minutes of this video, and I'll give another one of those for the other 2 movies. Okay, so screen share, desktop. So one of the things they talk about in Gravity is a satellite collision. Where 2 satellites in orbit around the Earth collide with one another, and as a result of that, the debris cloud starts sweeping around the Earth, knocking out everything else. And this is actually a phenomenon that people have been aware of since the 1970s, where it's maybe has started to happen because we actually did have a satellite collision, I think, back in 2009, where if you have so much junk in low Earth orbit, and in this picture, this is a map of all the space debris that we currently have, and you can see that there's the geosynchronous ring, which is where your communication satellites are, and then around the Earth here, this is the low Earth orbit trash, and in low Earth orbit, things have gotten very, very crowded, and it's a somewhat dangerous environment from a space junk point of view. And what can happen is different satellites are rocketing past each other at 10,000 miles an hour, and that you will punch a hole in another satellite with the piece of junk. And it's really rare for these things to be moving at anything like the same speed. And they're moving in opposite directions at very high velocity, and they can do a lot of damage to one another. It's rare. It's very, very rare for space junk to hit anything, but it can happen. And the more stuff we have up there, the higher the risk of satellites colliding, of these space junk clouds colliding. So one of the things that they did very well in Gravity, it was they mentioned this. I don't think they called it Kessler syndrome, but that is the name for it. And the whole plot revolves around it, because at the beginning of the movie, a satellite collides with another satellite, and the debris cloud just keeps sweeping around every 90 minutes or 45 minutes. It should be 90 minutes, punching holes in whatever they're trying to live on. So it hits the space shuttle, it hits the International Space Station, it hits the Chinese space station. But the debris cloud keeps coming around every 90 minutes. So they'll have sort of 90 minutes to like sort through all the damage and try to come up with a plan to get back to Earth, and then the debris cloud comes around again. And at the end, after the first sweep, everyone on the space shuttle is dead. The only 2 survivors are Sandra Bullock and George Clooney, whose character names I forget, so we will refer to them as Sandra Bullock and George Clooney from here on. And 2 other things that they do wrong in the movie. First of all, the chain reaction happens probably much faster than would happen in real life. The chain reaction where the debris cloud starts taking out other satellites or start taking out other satellites, that probably wouldn't happen quite that fast in real life. You'd probably have a week or 2 before all your communication satellites went down. Also, Sandra Bullock and George Clooney then proceed to go on a tour of the space shuttle, the International Space Station, and the Chinese space station, one after the other. And this is completely unrealistic. Yes, they're all up there. Yes, they're all in low Earth orbit. Oh, and the Hubble telescope as well. None of them are in aligned orbits. They never see each other. The space shuttle can go from one to the other, but it's a very complicated maneuver. You have to have planned it in advance. And it's basically like jumping from a running train, a racing train that's racing in one direction, onto a train that's racing in the other direction. Full speed, and you're going to jump from one to the other. It's not going to work out well for you. And that's basically what they're doing every time they hop from one to the other. And also these things usually aren't anywhere near each other in space. So that's a flaw of the movie. Another flaw of the movie, which actually really kind of annoys me, is George Clooney's character. Okay, this is the spoiler. Skip the next minute. Okay, George Clooney's character dies in the movie, and he didn't need to, because if you watch the scene where he dies in the movie, he hits the end of a line, and he's pulling Sandra with him, and she's tangled up in like a parachute or something, and he's pulling with her into the depths of space, and if they both go, all hope is lost. So he cuts the line and sacrifices himself so that she can make it back to Earth. And it's very noble, and it makes no sense physically. There's no physical reason why this force just keeps pulling on him. Once he hits the end of the line that's tying them together, he should then bounce back towards her, because equal and opposite reactions. Instead, he keeps being tugged out into the vacuum by some unknown force that I don't know. And so he fundamentally dies for a pointless reason, and the pointless reason is because they wanted him to die in the movie. And it's really, and have a noble sacrifice. Physically, it makes no sense. It upsets me every time I see it. Still upset. Am I still upset now? Yes. Just checked. Yep, still upset. Okay, moving on. I'm going to move on to Star Wars now. Star Wars. So I'm going to concentrate on The Force Awakens a little bit and on the original Star Wars. In The Force Awakens, one of the flaws of Star Wars that I, sort of overlooked in the original trilogy and maybe even in the prequels is that they don't really have a good grasp of the distance between planets or light travel time. So yes, okay, the Millennium Falcon can jump from system to system using hyperspace, and which is equivalent to Star Trek's warp drive. And okay, we have no idea how that works, because we certainly don't know how to travel faster than light currently. Currently, the laws of relativity are absolute. And they have another approach to it in Interstellar, where they use wormholes. But fundamentally, okay, this is new physics. And so you're allowed to break the rules. That's cool. Nevertheless, things seem to be very close. Star systems seem to be very close together in Star Wars. And in Empire Strikes Back, the whole plot hinges around the fact that the hyperdrive of the Millennium Falcon doesn't work. So they have to find a safe port. And how long do they actually fly from the planet Hoth to Cloud City? Was it months? Were they actually in space for years? Because if you were to try to do it today, fly from Earth to Alpha Centauri, it's going to take you traveling at most of the speed of light 4 years. Minimum time. Traveling at anything like the speeds we can achieve right now, it's going to take you something like 10,000 years. So light travel time in general, kind of a fuzzy idea in Star Wars. Then they start destroying planets, because it's a Star Wars movie, so they have to destroy planets. In The Force Awakens, they have Starkiller Base, which is the latest Death Star. So we're on Death Star Mark III now, I don't know. And it actually is capable of sucking in a star and spitting it out as death rays. And they actually kill off not just one planet, but like 5 at once. So here's a picture of Starkiller Base in operation, nuking 1, 2, 3, 4 planets at once. And that's cool. That's very explosive. You should not be able to see one planet being blown up from another in anything like the same kind of time scale. What is the light travel time between planets? Frank, Becky, or Brent? What's the light travel time to see Mars being blown up from the Earth?
Was it anywhere between 8 and 14 minutes, right?
Yeah, so but that's not going to be very convenient if we have to wait 8 minutes to see every single planet get blown up. So, not only that, but everyone in the galaxy is able to see this simultaneously. They all just step out of their houses and they look up and they can see this system being blown up. So, I don't know how far this system is from everybody else, 200 light years, 1,000 light years, but you just walk out your door and you see it being blown up. So, it's Star Wars. I'm pretty forgiving of a lot of things in Star Wars, but this one bothered me every time. Star Wars plays fast and loose with both vacuum and with gravity. And I didn't talk about the vacuum. I'll post it online with some more of these details. But gravity is one of the interesting things in Star Wars, because everyone seems to always be wandering around in about 1 g worth of gravity. So this is a famous scene from the original Star Wars movie in which Han Solo and Luke Skywalker are on the Millennium Falcon, and they fire their little Millennium Falcon guns at the TIE fighters to escape from the Death Star. I want you to watch the gravity just for a second. Watch where Han and Luke are standing in this first floor, the main floor of the Millennium Falcon, and then watch where they go. He goes up the ladder. Luke goes down the ladder, and then they sit down in their seats and they are calling back and forth to each other. What did gravity just do there? Does anybody know? So, yeah, I don't know. Frank, do you have any physics that could explain that? And that's also in the new movie.
I'd say the same stuff that
Powers the Starkiller base?
It was in Gravity that pulled
Oh, right.
pulled them away.
Okay. So that's Star Wars, but it's at a lower bar. So it's a funny little feature that if you watch The Force Awakens, they do the same thing, but this time it's only Finn shooting the gun. So you don't get the up the ladder, down the ladder, and then they call across from each other. Finn goes down the ladder, and then he's sitting in the same position I think Luke is in the first movie, but you don't necessarily see the gravity thing happen. But it happens all over Star Wars. The Death Star, gravity points north to south instead of into the Death Star. There's all sorts of weird things like that. Moving on to Interstellar. So I didn't really have high expectations for Interstellar after being disappointed by Gravity. And there are problems with Interstellar, starting with the fact that it has a planet in orbit around a black hole, which is a really cool plot point if you forget all of your physics briefly. So first of all, where is the light coming from that makes this planet has a liquid water ocean covering it, so it's getting a lot of heat. It's a habitable planet, sort of, which is warm enough to have liquid water on it. But it's orbiting a black hole. Typically you need radiation, and lots of it, to have a liquid water ocean. So you need to be in a sort of happy Goldilocks zone like the Earth is. And so this planet is sort of in a Goldilocks zone around this black hole, where black holes don't emit light. So black holes do emit light. They usually have accretion disks around them. In the movie, they have some kind of comment about how once the star collapsed, the light from the supernova, from the dying star, was trapped forever. And so you could always see it, but it was never ever going to quite escape completely. But that light would be very red, very, very red. Whereas black holes usually have accretion disks surrounding them, where stuff that they have pulled in is about to fall into the black hole. And again, it's always about to fall into the black hole, never quite does, from the point of view of anyone outside of it. And that accretion disk, which is viewed here, usually this is not the right color. Usually these accretion disks are emitting copious amounts of ultraviolet and X-ray radiation, none of which are healthy for life. So this planet, if it were actually in that orbit, first of all, it would be pulled apart by the tidal forces of the black hole. Second of all, it would be sterilized by the radiation. So unfortunately, the really cool planet that they visit, where 1 hour of time, every hour of time they spend on the planet, equates to 7 years of time back on Earth, even though that's a totally awesome concept, totally impractical. That said, that actually kind of is what a black hole, a supermassive black hole accretion disk would look like. If you watch Interstellar, it's actually worth reading the Wikipedia article on supermassive black holes, because supermassive black holes actually are the one black hole that you can fall into. Spoiler alert, Matthew McConaughey, Cooper, falls into the black hole at the end, and he doesn't get torn apart, which you would if you fell into a stellar mass black hole. Supermassive black holes, they have a tidal pull as you're passing the event horizon that's comparable to what you feel just standing on Earth, the difference between your feet and your head. And so he wouldn't necessarily die. The accretion disk should have nuked him with all those X-rays, but fine, okay. So he then falls into the black hole at the end of the movie. And this is actually what a black hole we think would look like because of relativity. bending, lensing the light around the black hole from the accretion disk. This is what an accretion disk around a black hole looks like to a person standing away from a black hole, which is totally what they did in Interstellar. I'll post some links to the debate between Phil Plait and Kip Thorne. They never actually debated. But, you know, Kip Thorne consulted on the movie. He feels the physics pretty solid. Phil Plait watched the movie. He hated it. So I'll post some links in the forum if you're interested in that, on what each one of them thought was right and which one thought was wrong. But I actually was pretty impressed just with what they did get right with relativity. So that was cool. It was cool. All right, I'm all done.
All right. Oh, that was great. Thank you, Jackie. You had that turn of phrase. I love that one. The rules of relativity are absolute. I thought that was great. Good. We have 4 minutes. Does anybody have anything in particular you wanted to say? Hi, Becky.
Hi.
We did good.
Can't think of anything in the 4 minutes. I didn't see the questions though.
I think we caught them.
Okay.
We covered them all.
Um,
That's cool. You were on the last Google Hangout. You did a lot there, so it all works out. Okay. I think that will do then. I don't see any other questions coming over. All right, so we will end this one off. AST 111X, thank you very much for hanging out for this past hour. Covered a lot of ground. If you have any questions about any of it or other questions, go ahead and ask in our discussion forum, and we'd be happy to answer them. All right, thank you, everyone. Bye-bye.
Thanks. See ya.
bye.